In exercise 17, it says, cyclopentanone was treated with lithium aluminum hydride, followed by H3O+. Explain what you would look for in the IR spectrum of the product to verify that the expected reaction had occurred, and identify which signal should be present and which signal should be absent if the reaction goes to completion. Alright, well, the first thing to do here is to draw the reagents or the reactants. We'll figure out how they react with each other to produce a product, and then we'll compare the reactant with the product. Cyclopentanone. Well, pent, that means we're dealing with 5 carbons, and cyclo means they're going in a ring, so it'll look a little bit like a pentagon. AN means all single bonds, and that suffix ONE means you have a ketone. Remember, a ketone is when you have a carbon double bonded to an oxygen and a carbon on both sides. So that, you could put that anywhere. I'm going to put it at the top. In general, anything that has a ketone ends in ONE. So for example, testosterone is called testosterone. It has that ending because it has a ketone in it. Alright, so that's cyclopentanone, and we're going to react that with lithium aluminum hydride. Now, you see lithium and aluminum, and instantly your first thought should be, oh my gosh, metals. These things are not going to be electronegative. They're going to give their electrons to whatever is left. Hydride, hydrogen. And that's going to act as a nucleophile. So what this looks like, and usually your book gives you this to you as LaH, lithium aluminum hydride. Another way you may see it is LiAlH4. That gives you more of an idea of what it looks like. You have an aluminum in the center bonded to 4 hydrogens. Aluminum, metal, and so it has very low electronegativity. It gives its electrons away and becomes slightly positive. What does it give its electrons to? All of the other hydrogens. And so hydrogen, which you don't normally think of as an electronegative element, becomes a nucleophile, slightly negative. Now that whole thing has a negative charge, and lithium is there just to balance it out so the molecule doesn't explode while it's in a jar on a shelf. So that's just there to balance that negative charge. Once you put it into solution, the lithium is going to go off and contemplate its life. So when this lithium aluminum hydride comes into contact with our cyclopentanone, what's going to happen? Well, for that, we have to identify the nucleophilic and electrophilic centers on cyclopentanone. Now, we have a very electronegative atom, oxygen, that steals electrons for itself, becomes slightly negative. Whatever it's bonded to becomes slightly positive. That's this carbon here. And so if the hydrogens are going to be our nucleophiles, what will they want to attack? They're going to pick their electrons up and attack that slightly positive carbon there. And the pi bond, the second bond here, goes toward the electrons in that pi bond go toward the more electronegative atom, the oxygen. And so what you end up with after that first step, I'll just have it going down here, is you have that 5-membered ring. That didn't change. Oops. That did not change. You still have a sigma bond to the oxygen. It's just now, whereas the oxygen had 2 lone pairs, now it has 3. 3 and a negative charge. And the hydrogen, there's a hydrogen here, that hydrogen that came from lithium aluminum hydride. But it's a bond line structure, so you don't have to draw that. Now that would be our final product, except it said it's followed by H3O+. So we'll take an H3O+ here. That's our H3O+. And of course the oxygen is electronegative, so all these hydrogens, all these hydrogens are losing electrons to the very electron-hungry oxygen. And so the hydrogens are slightly positive. And so this negative oxygen here on what was cyclopentanone, the electrons there are attracted to the hydrogens, they steal them, the electrons go toward the most electronegative place nearby, that's the oxygen, and so you end up with this molecule, which isn't, let me draw that a little bit better, this molecule, so you have your pentagon, and now you have that alcohol at the top. So this is actually I could even draw the bond there for you. That's cyclopentanol. That's what that is. All right, I'm going to erase the curved arrows in our original structure because now that we know what we're going to get, we want to compare our original structure in the orange here with our product structure in the blue. And how can we use IR spectroscopy to figure out whether our reactant turned into our product? Well, what functional group do you have that's different in the two molecules? In the first one, you have a ketone, the carbon double bonded to an oxygen. And if you recall, the shadow that casts is a sharp dip at around 1720 wave numbers. So our starting molecule will have a shadow at 1720 wave numbers. And our product has the alcohol. And if you recall, that the bond between the oxygen and the hydrogen of that alcohol, that casts a shadow, a smooth, broad shadow, between 3200 and 3600 wave numbers. So how would you know if the reaction happened? Well, you would look for the disappearance of the shadow at 1720. If all of this reactant truly turns into the product, you won't have this shadow at 1720 anymore. And you'd look for the appearance of this smooth, broad spectrum that would spread out between 3200 and 3600. So if those two things happen, then this reaction would have been complete. And you can use IR spectroscopy to track it.